we introduce our work, Coupled Iterative Refinement for 6D Multi-Object Pose, published at CVPR 2022. We address the task of 6D multi-object pose. Given a set of known 3D objects and an RGB or RGB-D input image, we detect and estimate the rotation and translation of each visible object. Given an input image, we first produce a set of object candidates using a mask RCNN. Since a canonical point cloud for each object is known during inference, we infer a 3D translation by aligning the projection of the point cloud with the predicted bounding box. We then render the point cloud using the predicted translation, concatenate the input image, and directly regress an initial rotation estimate and an update to the translation. We call the resulting pose estimate G0. Our primary contribution is the pose refinement step. Starting from our initial pose estimate G0, we render the object at G0 as well as several additional views at known perturbations around it. These perturbations are a hyperparameter chosen empirically. Our method works by estimating optical flow between each render and the input image, and then solves for the pose update which best explains that prediction. To do this, we first extract correlation features from each pair of images representing their visual similarity. We also predict a hidden state, which, together with the correlation features, are used to predict an update to the expected correspondence as well as per pixel confidence weights. We then solve for an update to the pose of the object that best explains the predicted flow for each image render pair. The solver also tries to align the depth in the renders with the sensor depth for the input image, which is not depicted here. The pose update is then applied to the current pose estimate using retraction on the SE3 manifold. This new pose estimate induces a new flow field from which we can predict a new flow update. We can repeat this entire process until it eventually converges. We also supervise on both the predicted correspondence as well as each pose update in order to encourage the process to converge to a good solution. It's worth highlighting that the flow between the image and each render is computed in both the forward and backward directions in order to maximize the number of matches, which we show empirically to be important. Our pose refinement method, including the solver, are fully differentiable. The solver gradients enable our method to learn to predict confidence weights for each flow vector, which guide the solution to the optimization objective. This is important for outlier rejection and the exclusion of pixels which don't have a visible match in the other image due to self-occlusion or occlusion from other objects. Traditionally, outlier rejection is achieved using ransack-based perspective endpoint solvers, but the gradients from ransack-based methods are usually ineffective for learning. In practice, our method tends to give lower confidence for featureless surfaces, since their exact match is usually difficult to predict. In the paper, we show that this weighting scheme improves results across the board compared to the usual approach of treating all matches as equally important in the optimization. We also introduce a variant of our method designed to operate on images without sensor depth. Rather than relying on sensor depth, we render the object at the predicted pose to produce a depth map and proceed as if we have RGB-D input. However, this basic approach is not mathematically sound because the render depth is now a function of the object pose, but is still treated as a constant in pose optimization. On the other hand, a fully principled treatment is difficult to implement because it requires computing the Jacobian of the rendering function as well as the derivatives of the Jacobian during backpropagation. As a middle ground, we use the render depth to linearize the optimization objective and introduce depth as a separate variable in the optimization so that we jointly optimize both pose and depth. Since the updated depth is now potentially inconsistent with the updated pose, we discard the depth update and render a new depth map in the next update iteration. We show in the paper that this approach gives good results. Our method achieves higher accuracy than all prior work on the BOP benchmark, which consists of evaluation across several different datasets. Our RGB-only variant is competitive with the best prior work that also doesn't use sensor depth as input. Full results are in the paper and on the official BOP benchmark leaderboard. On GitHub, we provide training and testing code to reproduce our work, as well as off-the-shelf demos. Thank you.